The world of shipping is on the verge of a revolution, and it's coming from China. Imagine a giant cargo ship big enough to carry 14,000 standard shipping containers, slicing through the ocean waves. Now imagine that this ship doesn't need to stop for fuel. Not for a week, not for a month, but for an entire decade. This isn't science fiction. It's the bold new concept unveiled by engineers at China's Jiangnan Shipbuilding Group in November 2025. This vessel represents a monumental leap forward in maritime technology, promising to reshape how goods are transported across our planet. It's a game changer because it runs on nuclear power, but not the kind you might be thinking of. So, what makes this ship so special? It's not just its size or its incredible endurance. The real breakthrough lies in its power source, an advanced thorium-based molten salt reactor. This cutting-edge technology allows the ship to operate continuously for 10 years, eliminating the need for frequent and costly refueling stops that plague today's massive container fleets. The ship could travel millions of miles, connecting continents without ever pausing to take on more fuel. This kind of efficiency and autonomy is unprecedented in commercial shipping. It opens up possibilities for faster, more direct trade routes and a truly global, non-stop logistics network. It's a vision for a world where goods move more freely and reliably than ever before. The environmental implications are just as profound. The global shipping industry is a major contributor to air pollution, responsible for about 3% of the world's carbon dioxide emissions. These conventional ships burn massive quantities of heavy fuel oil, releasing harmful pollutants into our atmosphere and oceans. By switching to a clean nuclear energy source, this new Chinese cargo ship design offers a path toward decarbonizing one of the world's most essential industries. If this technology becomes widespread, it could significantly reduce the environmental footprint of global trade, helping us combat climate change and protect our planet's delicate ecosystems. It's a powerful example of how innovative engineering can provide solutions to some of our biggest challenges. This ambitious project is more than just an engineering marvel. It's a strategic move by China to lead in both maritime technology and sustainable energy. By pioneering the use of thorium reactors in commercial vessels, China is positioning itself at the forefront of a new era. The ship's design, revealed in detail by Chief Engineer Hu Kei, showcases a commitment to pushing the boundaries of what is possible. While it is still a concept, with construction yet to begin, the detailed planning and the successful testing of a land-based prototype reactor in the Gobi Desert show that this is a serious endeavor. The world is watching as this vision for a cleaner, more efficient shipping future begins to take shape. At the core of this incredible ship is its power plant, a thorium-based molten salt reactor, or TMSR. This is a very different kind of nuclear technology compared to the uranium-based reactors used in older power plants and submarines. Instead of solid fuel rods, this reactor uses a liquid fuel. Thorium, a naturally abundant element, is mixed into a molten salt that flows through the reactor's core. As the thorium undergoes a nuclear reaction, it releases an immense amount of heat. This process is far more efficient at using its fuel than traditional reactors, meaning it produces very little waste for the enormous amount of energy it generates. It's an elegant solution to a complex problem. So, how does this heat become electricity to power the ship? The reactor's heat, reaching very high temperatures, is used to heat up supercritical carbon dioxide, or SCO2. Supercritical CO2 is a state of matter where it acts like both a liquid and a gas, making it incredibly good at transferring energy. This hot, high-pressure SCO2 then spins a turbine, which is connected to a generator. This process, known as the Brayton cycle, is remarkably efficient. It converts about 45 to 50% of the reactor's heat into usable electricity. To put that in perspective, conventional steam-based systems in older nuclear plants typically have an efficiency of only around 33%. This higher efficiency means more power from less fuel. One of the most innovative aspects of this design is its operational life cycle. The entire reactor is designed as a sealed, self-contained module. Think of it like a giant, long-lasting battery. This module is installed on the ship and provides continuous power for its entire 10-year operational period. At the end of that decade, the ship doesn't get refueled in the traditional sense. Instead, the entire spent reactor module is removed in one piece and replaced with a brand new one. This approach simplifies maintenance, reduces the risk of nuclear material proliferation, and minimizes the crew's exposure to radioactive components. It's a plug-and-play system for nuclear power. The fuel choice itself is also strategic. Thorium is much more abundant in nature than the uranium used in most nuclear reactors, and China has significant domestic reserves. This reduces reliance on foreign energy sources and creates a more secure fuel supply chain. Furthermore, the land-based prototype of this very reactor, located in China's Gobi Desert, has already proven that the technology works. In 2025, it achieved long-term stable operation and successfully demonstrated the process of converting thorium into the fissile material needed for the reaction. This successful test provided the crucial proof of concept needed to move forward with designing the maritime version for this game-changing cargo ship. When people hear the words nuclear power, safety is often the first thing that comes to mind. The designers of this thorium molten salt reactor have made safety a top priority, engineering a system that avoids the dangers associated with older nuclear technologies. One of the biggest differences is that this reactor operates at normal atmospheric pressure. Conventional uranium reactors use water as a coolant, which must be kept under extremely high pressure to prevent it from boiling. If a leak occurs in those systems, the sudden drop in pressure can cause an explosive release of radioactive steam. The molten salt reactor doesn't need high pressure, completely eliminating that specific risk of explosion. Another key safety feature is what scientists call a strong negative temperature coefficient. This sounds complicated, but it's a simple and brilliant concept. It means the reactor regulates itself. If the reactor starts to get too hot, the nuclear reaction automatically slows down. If it cools off, the reaction speeds up. This is a natural physics-based property of the molten salt fuel itself, not something that relies on complex computer systems or human operators. This inherent stability prevents the possibility of a runaway chain reaction or meltdown, which was a major concern with older reactor designs like the one at Chernobyl. It's like having a built-in, automatic brake that can't fail. The safety systems don't stop there. The designers have included multiple passive cooling systems. Passive means they work automatically without needing any electricity or human intervention. In the event of a complete power failure on the ship, these systems would kick in to draw heat away from the reactor core, preventing it from overheating. It's a bit like how a thermos keeps your soup hot without being plugged in, but in reverse. It uses natural processes like convection to keep things cool and stable. These redundant layers of safety ensure that the reactor remains under control even in the most unlikely emergency scenarios, providing peace of mind for the crew and the public. Perhaps the most ingenious safety measure is the fail-safe drain tank. In the absolute worst-case scenario, where all other systems fail, a special plug at the bottom of the reactor, made of a frozen salt, is designed to melt. When it melts, all the liquid molten salt fuel would automatically drain into a secure containment chamber located underneath the reactor. Once in this chamber, the fuel would spread out, cool down, and solidify into a solid block. This process traps all the radioactive materials safely within the hardened salt, preventing them from ever leaking into the environment. It is a final foolproof mechanism that ensures the reactor will always fail safely. The potential benefits of this nuclear-powered cargo ship are enormous, especially for our planet's health. The global shipping industry is a behemoth, moving over 80% of the world's trade by volume. But this comes at a high environmental cost, with the fleet of over 50,000 commercial ships burning vast amounts of fossil fuels. Adopting thorium reactor technology on a large scale could slash the industry's carbon emissions, making a significant dent in the fight against climate change. Cleaner air, healthier oceans, and a more stable climate are all part of the promise. This ship isn't just about moving boxes from one port to another, it's about pioneering a sustainable path forward for an entire industry. However, the journey from a concept on a drawing board to a fleet of nuclear ships sailing the high seas is filled with major challenges. The first and most obvious hurdle is the cost. Building a ship with a state-of-the-art nuclear reactor is expected to be significantly more expensive than constructing a conventional vessel. While the long-term savings on fuel would be substantial, the high upfront investment could make shipowners hesitant to adopt the technology without strong government incentives or subsidies. This economic barrier is a serious consideration that will need to be addressed before these ships can become a common sight in our oceans. Beyond the financial costs, there's a mountain of regulatory hurdles to climb. Currently, there are no comprehensive international rules for commercial nuclear-powered ships, the International Maritime Organization, or IMO, would need to develop a whole new framework covering everything from construction standards and crew training to insurance liability and port access protocols. Many countries and port authorities may be reluctant to allow nuclear vessels to dock near their cities without clear and robust safety guarantees. Establishing these international agreements will be a complex and time-consuming diplomatic process, requiring cooperation and trust among nations around the globe. Despite these obstacles, the potential impact of China's nuclear cargo ship concept cannot be overstated. If successful, it could fundamentally change global shipping, giving China a strategic advantage in maritime trade, and setting a new global standard for clean energy at sea. It forces the world to confront important questions about the future of energy, trade, and environmental stewardship. This project is a bold declaration that a zero-emission shipping industry is not just a dream, but a tangible goal. The path is difficult, but the destination, a world with cleaner, faster, and more efficient global trade, is a powerful motivator for this incredible journey of innovation.